Dear students, I welcome all of you for today's session. And the session is on performance analysis of an algorithm. So, what is an objective of this session? Okay, so suppose you people are given some problem. What you will do, you will go through the problem statement, you will understand what actually the problem is, then you will think of how to solve that problem, right? Later, you will come up with a solution, and the solution is nothing but an algorithm. So all of you will come with their own strategy, with their own solution, with their own algorithm. Now the question arises, whose algorithm is the best? If not the best, better. Okay. So here the question comes analysis of an algorithm. Here the analysis of an algorithm means how efficient is one algorithm when compared to the other algorithm. Okay. So to check the performance of an algorithm, there are two criteria we need to know. Okay, those we are going to discuss in this session. Thus, I mean to say, the first criteria is that what is the space required by your algorithm? Got it? And the second is how fast your algorithm runs. Got it? So now, these are the two things what we are going to study in this session, and we'll look at some example. Okay, so now coming to the contents. So I said the first object is I will introduce you to performance analysis. Okay, so performance analysis means here I'm going to tell you about what is space complexity or time complexity. Then in detail we'll have a look at the space complexity and time complexity. At the last, we'll have very important topic, what is known as orders of truth. Okay, and the last topic is very important, and that is the core of this subject, design and analysis of algorithm. Now, coming to first topic, that is performance analysis. So, what actually performance analysis? I said is nothing but judging the means investigating how efficient is the proposed solution. I mean the proposed algorithm. You are given, you are suggested some solution for the problem what I have given to you, right? And now I want to investigate how efficient is your algorithm compared to your friends. Got it? So I said there are two criteria. One is space complexity. Space complexity. The space complexity of an algorithm is nothing but the amount of memory it needs to run to completion. Got it? I said the space your algorithm occupies in memory for complete execution. Okay. If lesser the space occupied by your algorithm, I'm going to say your algorithm is best. Got it? Now coming to time complexity, what I said, the space complexity, lesser the space consumed by your algorithm, I'm going to say your algorithm is the best. Okay. So now coming to time, okay, how fast your algorithm runs. For the same problem, you guys are come with your own solutions, so your own algorithms. Okay. Now to say whose algorithm is best, I'm going to tell the one whose algorithm is going to consume less time. Got it? So this is about how we are going to investigate the efficiency of an algorithm. Got it? The two things are space complexity and time complexity. Now we'll have a look at space complexity in detail. Okay. Just have a look at the slide. Think all of you are viewing this two algorithms displayed on the slide clearly, right? Okay. Now before I say what the space this two algorithm is going to consume, okay, is going to occupy for their execution. Let me tell you the difference between these two algorithms. Look at the first algorithm. There's only one statement return. Got it? And when I look at the first algorithm, I know there are three variables, A, B, and C. Okay. Let these three variables be of any type, maybe an int, maybe float or string, whatever it be. Okay. So in general, let me treat these variables as a generic now, as of type generic. Got it? Let me say 1 unit of memory is required for one variable A. Got it? So since there are three variables in your in the first algorithm, so what we will come to know, since each require 1 unit of memory, so all these three totally this three variables require 3 units of memory. Got it? So apart from these three variables, I can see there's a constant 4. Okay, we need not have to worry about that. Okay, so I mean you are very clear in first algorithm there are only three variables. If assuming each variable require 1 unit of memory, so at least minimum 3 units of memory required by this algorithm. Now look at the second algorithm. Okay, in the second algorithm, what you can see, there are some variables. Okay, we'll say yes, got it, and you can see even a variable I. You can see even a variable n. So yes, I, n each require 1 byte of memory. So, but what actually you can see here, there's also an array A. So now the question is that how much unit of memory is going to be occupied by this array A? Got it? So can anyone tell me? Okay, just think of it. Okay, or in each run, whether this array A is going to occupy the same bytes of memory or same units of memory? I mean, let me say the algorithm is to determine sum of array elements. Okay, I mean when you run this algorithm for the first time, you must give 10 elements in an array. Got it? So in the next run, you might give 100 elements as an array. Got it? In the other run, you might give 50 elements in an array. I mean to say, in this second algorithm, when you compare with the first algorithm, okay, here there are no, there are apart from variables like A, B, C, here S, I, N, there is a variable there that is nothing but an array whose size is going to vary in each execution, because the size of the array is going to vary, because in each execution I may give any number of elements, right? So clear. So in this case, what happens? Suppose assume in one run there are 10 elements in array. Got it? So each element require 1 units of memory, right? 1 units of memory. So 10 elements require 10 units of memory. Got it? So apart from 10 elements, yes, I and each occupy one byte. Oh, sorry, 1 unit of memory. So totally in this algorithm, in this run, it occupies 3 plus 10. Clear? Units and 3 plus 10 units of memory. So in the second instance, okay, second run, suppose if I give 50 as an array element, in that case, the number of units of memory required is 3 plus 50. In the third run, if I give 100 elements, then in that case 3 plus 100 units of memory. So in general, what I can say for the second algorithm, the space is occupied are 3 plus n units of memory, where n is nothing but number of elements in that particular run in an array. Got it? So I mean, so space complexity, when we study about space complexity, we need to look at two things. Okay, I said like in my program, in this two algorithm, you are just very clear. There are two parts. One is the fixed part, like SIN, means the space required by SIN. Got it? Are always 1 units of memory in each run. Whereas the space that is going to be occupied by array is going to vary in each run. So there are the second part is that there's a variable part too. Got it? Clear? So In general, now I will look at I said there are two parts, fixed part as well as varying part in each algorithm. So in general, what I can say, I suppose C is the fixed part, okay, and SP, let me say SP is an is a varying part. I mean to say, suppose in my first run, if I say array contains 10 elements, then SP is equal to 10. In next run, if I say array contains 50 elements, SP is nothing but 50. In the third case, if I say array contains 100 elements, SP is 100. Okay. So in general, what I can say, space requirement is nothing but S of P equals C plus SP. Got it? Clear with this? So now let me proceed with the time complexity. Okay. Now let me see. And time complexity, let me say in any algorithm, okay, in any solution, okay. Uh, there may be any number of additions, there may be any number of subtraction, there may be any number of multiplication, there may be any number of divisions, as well as some other operations. And assume ADD of n. Okay, I mean to say ADD is a function that gives the number of additions involved in this particular algorithm. Similarly, SUB is a function that gives number of subtractions involved in an algorithm. MUL is a function that gives number of multiplications involved in an algorithm. DAV is a function that gives number of divisions involved in an algorithm. Okay. So let CA, okay, as you can look in the slide, I guess let CA be the time for one addition on one specific computer. I say specific. CA is dependent here, but whereas number of additions, subtractions, multiplication, divisions are always same in one particular algorithm, we'll assume CA, the time for one addition, varies from machine to machine because of their processor speed, okay, varying in processor speed and other hardware characteristics. So I repeat, time for one addition, that is CA, one subtraction CS, CM, CD, they are machine dependent. Got it? So here, but suppose if I know the time for one addition, time for one subtraction, one multiplication, one division, then what I can say when I run on that particular machine, the time taken for that algorithm, that is TP of n, is nothing but given this expression, CA into add of n plus CS into sub of n plus CM into mul of n plus CD into division of n. So now this is how we can compute the time taken by an algorithm. But what actually drawback here means, let me say, assume, listen carefully, you have designed an algorithm, okay, you have implemented it as a C program. Today, you are going to run that program in one of the system in your lab. It might take some X seconds. Tomorrow, you're going to run the same program with the same input in some other machine. It may take the time taken by it, maybe is going to differ from the time what you have seen in the previous run on some other machine. And similarly, if you run the same program with the same input in your laptop, the time might be something. Got it? Means what you're going to see for the same program, for the same input, time on different machines got varied. So suppose in your exam now, you will be asked a question, what is the time taken for that particular problem with that particular input? What is your answer? Because you have run on 3 different machines, you got 3 answers. You mean you're going to say 3 times? Got it? So real time, I discussed in the previous session also, they are machine dependent. Got it? So what we can't say 3 answers for one problem, right? So what we need, rather than real time, we are going to have a solution so that each and every students will say only one answer, and that answer should be independent. It should be independent of any machine, any hardware architecture. Got it? So what is that metric? Independent metric is something we'll discuss now. What I call it's a step count, or I'll call it's an operation count. First, let me tell you what actually means here, like in that expression, okay. What I'm going to say, just I'm going to give the number of statements, total statements in the program we are going to see. Okay, time complexity here, I'm not going to say in terms of seconds or microseconds, nanoseconds. Time complexity, I will measure in terms of independent metric. Independent metric, and that is nothing but we call something as a step count or operation count. Okay, means total will still look at total number of steps in my program, and let me say this is the timetable, because let me determine number of steps, and let me tell that number of steps in the program is nothing but its time complexity. Now, how to determine this number of steps? There are two methods. Okay, I'll discuss that, but before that, I'll make you familiar with the step count. Okay, what is the time complexity? I said in terms of number of steps, right? So let me have a look at the slide, and we'll come to that. Now, look here. I'll come back to previous two slides, but I will look at this algorithm at present. Okay, look at this algorithm. Okay, again, there is to determine sum of array elements. Okay, so how many steps are there? What actually step? Okay, a step. A program step is a loosely defined, syntactically or semantically meaningful segment of a program that has an execution time that is independent of the instance characteristics. Got it? So I mean to say, in my program, I may use some assignment statement, may use some expression statement. Got it? Or what you can see on the slide, there's something that's written a plus b into c plus some expression, right? Even this is statement. We know that something terminated by a semicolon, right? So that each and every statement we will call as a step. Got it? Clear with the step? Program step means each and every independent statement. So I need not every statement we call as a step. So time complexity, we need to determine number of steps. Okay. So now we'll look here. So now I will look at this algorithm carefully, and let me clear it total number of steps in this. Okay, let's see. The first statement is an assignment sum equal to 0. Clear? The second statement is for I equal 1tn. The third statement is sum equals sum plus AFI, and the fourth is return. But now I need to compute how many times each of the statement executes. Okay. So you run this algorithm any time. The first assignment statement sum equal to 0 in all run, it gets executed only once, and it's very clear, right? Clear? Sum equal to 0 will be a run only once. No, and similarly, return statement, return sum, because it is out of the for loop, and even return sum is going to execute only one time. I will look at the last column. Okay, I will look at the last column. What I said, last column I said last of the last second column, frequency assignment sum equal to 0 is shown as 1 because in each run it exists only once, whereas return also a return statement exists only one in each run, so frequency is 1. Now what about second the other two statements, for and sum equals sum plus f? So one thing I'll tell you about first I'll tell you about sum equals sum plus f. So sum equals sum plus a of I will execute for each of the true conditions. Because I mean to say for each value of I starting from 1 to n. When I is 1, it's in within the range n. So sum equals sum plus a of I will execute. When I is 2, again sum equals sum plus a of I will execute. When I is 3, sum equals sum plus a of I is going to execute. Similarly, when I is n, sum equals sum plus a of I is going to execute. So sum equal to sum plus a of I is going to execute how many times? N times. So what about for statement? So in for, just have a look at the last column. I've shown as n plus 1, right? So you might have wondered that even for statement is going to execute n times, but why one extra time? Let me clarify, be cautious. So for statement, first means in this condition I am going to check, right? Initially I is 1, condition is true, once for got executed. Next case I is 2, condition is true, first statement got executed second time. When I is 3, condition is true, for got executed for third time. When I is n, condition was true, for got executed nth time. So now I becomes n plus 1, condition for got executed for the last time, but now control will come out of for loop because of condition false. Got it? So n plus 1 means n for the true conditions, that is I within the range 1 to n, and plus 1 is when I becomes n plus 1, that is a condition to come or to make control come out of for loop. So got it? So I will look at actually there are 4 steps. Okay, what are those? One is assignment, one is for, one is addition expression, then the return statement. So later we'll determine frequency, how many times each will execute. As sum equal to 0 exists 1 time, first statement n plus 1, additional expression n times, because it addition sum equals sum plus a for n times, because only for true condition, and return. So now at the last we'll compute. So 2n plus 3. This is what 2n plus 3 steps totally in this algorithm. Okay. So this is the time complexity we are going to measure. Clear with this? So now in this manually, I said to determine step count, there are 2 methods. I should have told earlier. The first method is using a global count variable in my program, and the other one is building a table. This method, what you are going to say, manually we are computing by ourselves. Given an algorithm, myself I'm going to compute total number of steps. Clear? Building a table, given an algorithm, myself I'm going to compute total number of steps. Okay. Suppose now let me say I don't want to compute myself. This 2n plus 3, what I got now, I don't want to compute myself. I want my algorithm itself should compute. Got it? I want this algorithm, sum of a comma n should itself compute this 2n plus 3 and return as an output. Got it? Getting my point? Algorithm, I want algorithm itself to compute this 2n plus 3. Okay, even that can be done. Okay, for that what we'll do, first I have designed an algorithm, then I'm going to make some modification on algorithm. Okay, I mean listen cautious, listen carefully. I will make use of one extra variable. I'll call it as a count. It's a global variable, initially initialized to 0. Okay, and what I'm going to do with this global variable count means, whenever an instruction gets executed, I will just increment the count by 1. Got it? I mean, in this program, there is one variable. First statement is sum equal to 0, right? I mean, when sum equal to 0 is going to be executed, this is the first step. Got executed, and that will be reflected in count by incrementing by 1. So next, for second time, next one for I equal 1 to n gets executed. Okay, when I equal to 1, true condition. There's a second step got executed. Again, now I'll increment count by 1. Next expression, sum equals sum plus a if I get executed, I'll increment count by 1. This I will do. Okay, so just have a look at previous line. Now see here, don't get confused. Okay, the same algorithm I modified using count, because I said here I want algorithm to give the total count. Okay, so you see here, just count is not a part of this algorithm. Remember, it's an extra variable I have used to compute the total number of steps. So see here, in this algorithm, you know, the first statement, here sum equal to 0, right? So immediately after sum equal to 0, I have used count equal to count plus 1. Got it? Why means sum equal to 0 got executed. I want that to reflect in a count by incrementing it 1. I've done it. So next, initially for I equals 1, first statement gets executed for I equal to 1. I equal to 1 is condition true. Now control where it goes, condition true means control enters the loop. So as soon as the control enters the loop, I want to reflect the execution of this for in a count. So first I'll use count equal to count plus. Got it? So now the execution of for when I is 1 is reflected in a count. So next expression sum equals sum plus CFI gets executed. So sum equals sum plus CFI got executed, right? And again I want this to reflect in count. So next I'm again incrementing count by. Clear with this? So now again I becomes 2, again condition I equal to 2 will be evaluated true. So again now control enters the loop for, right? Enters the loop. So I am reflecting this I equal to 2 in count by incrementing by 1. Now some statement gets executed. This again I will reflect it in count. So this happens for I equal for all I equal to n. So finally, when I becomes n plus 1, condition becomes false. So where I equal to n plus 1, condition becomes false. Now, control won't enter the loop. Where the control goes? Control goes out of the for loop. Out of the for loop. So this last execution of for, that is I equal to n plus 1, for which condition has become false, okay, should be reflected. So what I have used immediately out of the for loop, I have used one count statement, count equal count plus 1. Okay, even in the comment you can see that for execution of last for state. Okay, so what happened now? There's a return statement. Okay, well, now you might be wondered. In each case, after execution of a statement, I am using count equal to count plus 1. But why in case? But for in order to reflect for the execution of return statement, I have used count equal to count plus 1 before that. Because if you use the return statement, it goes out of the algorithm, right? So only in case of return, I am using count equal to count plus 1 early. Got it? So this is how to compute a step count of an algorithm. There, I repeat. I'll come back to previous slide. I said time complexity. Real time we are not going to consider because it's machine dependent. So we are going to have an independent metric, that is a program step count. There are two methods. One is just now I said modifying an algorithm using a count variable, and the other one manually I'm going to compute myself using this table. Okay, see, 1 second, let me come back. So what was the step count of this algorithm? We can see it's a 2n plus 3. So what type of function is 2n plus 3? We call it's a linear, right? It's a linear. Linear means, you know, right? N square we call quadratic, n cube cubic, 2 power n exponential. We have seen some function. Okay. Now we'll say. So how efficient is your algorithm? Is going to no, through its complex. Now here, what I say for this algorithm, I call the complexity is linear. Okay, expression or 2n plus 3, whatever it be, but the growth rate is linear. I call it a linear. So now let me look at orders of growth. Okay. So now what happens for each algorithm? Okay, I've given one problem to you guys. You have designed an algorithm, means you have come up with your own solutions. Okay, all of you have come up with your own solution. Next, I will determine this step count. Let me assume I have determined the step count of your algorithms. Okay, so what I'll see for some algorithm, for some of your solutions, I found it's a log n plus something something. I'll call it a logarithmic. Then 2n plus 3, some that will call a linear, and some will get n log n. Some will get n square. N square means quadratic. cubic, exponential, factorial. I mean, this in detail I'll tell you. How I written log n means I may get n means like this. Okay, in this 2n plus 3, right? I won't say it's a 2n plus 3. I just call it n. Actual count is 2n plus 3, but that count belongs to a function linear that we are going to use here. So means now suppose the one whose algorithm solution step count is log n, I will call this solution as the best one. Okay, and the linear, okay, n log n, okay, n square. Finally, the worst 2 to the power n factor, I call this solution to be the worst. Why? Now look at in this table. Let me say, look at the second column. Just have a look, second column. What happens? I've used now see that the second column 1, 2, 4, 8, 16. In each entry, I've just doubled, right? Previous first entry was 1. Second entry twice the previous, that is previous was 1, it becomes 2. Third entry twice the previous, that is 4. Fourth entry twice the previous, that is 8, 16, 32. Means suppose size of the problem I keep on increasing. Okay. What about the time it's going to take? This is what order of growth means. Suppose I'll run the program with some input. It is going to take some time. Next, I will run the same program with doubling the size of the input. Now, how much extra time is going to take? This is what order of growth. I repeat, order of growth means first we will run the algorithm, run the program with some input. Will not on the time. Now, next we'll double the input. What time it's going to take? We'll note how growth of the time varies with doubling the size of the input. That is orders of growth. So now just now look here in the first column log n. You just have a look. What happened? That entry just got incremented by 1, right? 0, 1, 2, 3, 4, 5. I mean to say, doubling the size of the input for an algorithm whose growth rate is logarithm just increases the step count by 1. Got it? If algorithm's efficiency is logarithmic, then doubling the size makes step count to get increased by just 1. Okay, whereas linear, same number, same as size. N log n, you can see just even that gets increased with 2, 0, 2, 8, 24, a minute. Okay, it's okay. Now, but whereas if the growth rate is an quadratic or cubic, you see, for doubling the size, the step count, okay, the entries here is nothing but step count. The entries in this table is nothing but step count. So what happens when I double the size? For cubic or quadratic and cubic, the step count got increased very fast. And you can see in case of exponential and factorial, the step count drastically increased for doubling the size. Got it? So I mean, if an algorithm's efficiency is logarithmic, I repeat, if the algorithm's efficiency is logarithmic, doubling the size of the input just increases step count by 1. Whereas exponential and factorial, it increases the step count drastically. So what you can say, drastic, if the step count got increased, of course, the time is going to consume also increases, right? Clear with this? So the best algorithm will always have efficiency logarithmic or linear or n log. When I say n square, n cube, they are better. Okay, not the best. They might be better, but exponential and factorial are the worst. Okay, so always if you want to compete, okay, you need to come up with a solution whose growth ratio will be logarithmic or linear or n log. Okay, if you have come up with quadratic or cubic, try to improve, make it logarithmic or linear and log. The same thing I've shown this graph. Okay, so the x represents size. Okay, whereas y represents some time. You can see, okay, log n always as the size increases, also the time it takes is less. It doesn't increase. Got it in the graph. But in the same graph, you can just say increase in the size, that exponential 2 power n and n factor n square I have not shown in fact 2 power n or n square. You just see the time drastically increased. Got it? So in the graph you can see increase in the size here. Just increase doesn't increase time much, whereas exponential increases the time drastically. Got it? Now let me take one example. Okay, with this. Okay, let me say in so let me have a look at the second example. First example is very clear. So let me say for some algorithm, the step count is of n into n minus 1. Of n into n minus 1 means of n square minus of n. Of n square, right? So what type of function is this? Quadratic. Now we have come up with a solution whose growth rate is quadratic. Got it? Reason quadratic. Now let me run with some size. It's going to take some time x. Let me assume it's going to take some time x. Now if I double the size, what time it's going to take compared to previous? So remember, I will use some expression t of 2n. You'll see here that the last t of 2n means n some n was some size. Okay, 2n I have used. So what it shows 4 times t of n means while solving you'll come to know when I double if the growth rate is quadratic, and if I double the size, the time it's going to take is 4 times the previous time. Got it? Now let me see here. Same thing here, n square. What you have seen 4 times the previous time, just 1. 4 into 1. 4 into 1 is nothing but 4. 4 into 4 is nothing but 16. 4 into 16, 64. 16 into 4, 16 into 4, 64. 64 into 4, 256. Same thing. Got it? So this is about today's session. Thank you for listening.